Multiplication. We were talking about multiplication because this guy is an eigenfunction to many operations, so we will eventually take it and multiply by constants that will come from the analysis of our operators. And this is what will happen. Each of these constants will just amplify or attenuate the signal and add or subtract some phase. So when the system is a system for which this guy is an eigenfunction, exponential goes in, exponential with same sigma and omega goes out with just different amplitude and different phase. But the rate of growth and the frequency will never change. Same for discrete exponentials. So now let's see the activity, continuous exponentials. This will seem a bit tricky, but it should be easy. Again, we use gdown to download the data. And we will download the samples of a continuous exponential. Continuous means that I'm using this notation. Of course, in the end, it's also discrete. So this guy is something times e to the st times u of t. There's a step multiplying here. This is why we see 0 for negative times. Now, when I download the data, I create the variable for sampling period, the time vector, the x vector for this signal. Now reproduce this signal using only exponentials times steps. Notice that this is the real part and the imaginary part is 0. How can we do it? How can be that an oscillating exponential is purely real? Because things oscillate when we have this different from 0, right? And when we have this different from 0, this guy is the rotating exponential, which has a real part and an imaginary part. So it's here. Is it possible that an exponential, a harmonic exponential, has only real part? No, it's not possible. But it's possible that a sum of two exponentials have only imaginary part. And this is what you have to do here. My suggestion is that you look at this as x of t equals some amplitude times some real exponential with decreasing or increasing. It's decreasing, so we know that this is smaller than, this is negative, times a cosine of omega t plus some phase. And this phase will be this guy, the phase of the complex number. Because if we take the Euler identity, sine of theta, we can also rearrange it to show that cosine of theta equals half e to the j theta minus e to the j plus e to the minus j theta. If you do this, if you input this here, what will happen? You will have x of t equals this e to the st half e to the j omega t plus now this guy again half to the minus j omega t plus this. You will have two exponentials, and you work them, and they are sigma. Here we have sigma, right? Or S. Sigma. It's sigma here, sigma here. They are, in fact, complex conjugates, right? Here I have some angle. Here I have the same angle with an inverted sign. And when I add two numbers that are complex conjugates, with angle minus here, and angle plus here, they add up to something real with twice the real part and nothing in imaginary. So these two guys will add up to something real. That's how I suggest you to solve this problem. You find these parameters, sigma, omega, phase for a cosine. And then you do this, and you will find the exponentials that you need to cast the signal in this form. Because at the end, you can only use the function numpy.exp times some u of t that you have to define. We did it last class. You can check the video to get back to it. So, in the end of the day, you will be summing two complex signals with real and imaginary non-zero components, and they have to add up to something purely real. Then you plot both in the same graph to show that you found the right parameters. Okay, that's it with complex exponentials continuous case.